It's on several occasions already that I had the pleasure and privilege of introducing our speaker today, Professor Luiz Davidovich, here in this room, in this audience. But each time you can tell a different story. Luiz is a legend, living legend of this field, and so each time you can tell a different story, and it will still be about this researcher, this nice person, and it will sound differently. And of course, the formal part, Luiz Davidovich is the pioneer of the field of quantum physics, quantum optics. He contributed tremendously, enormously to different areas of the field. He got his PhD at the University of Rochester, and then he continued with his career at different universities and institutes, including the University of Rochester, ETH in Zurich, and then of course in different places in Brazil. And Luiz is the member of the Brazilian Academy of Sciences for a long period of time. He has been serving as the president of the Brazilian Academy of Sciences. He is the member of the National Academy of Sciences of the United States, and he is a member of many other Academy of Sciences, Academy of Sciences for the Developing World. He is the winner and the winner of the most prestigious and important national and international awards, including the Grand Cross of the National Order of Scientific Merit and the Brazilian National Prize of Science and Technology. And again, this list goes on infinitely. Now, as far as his scientific legacy is concerned, is tremendous. For example, his story of the sudden death of entanglement has been cited. So this is a sad story of sudden death of entanglement. Has been retold in generations. It has been recited more than 1,000 times. And of course, his review of quantum handle works with Aronoff and Zegri has been cited almost 2,000 times.
Okay, so I'm very happy to be here again, and for some of you, this is not really be a full new story. I'm going to repeat things that I have said here in the past, so that this becomes a consistent presentation. However, I hope that even the things that I told you in the past, I'll try to present today in a different way. Okay, so that we have another look at the basics of quantum metrology. Now, this is the roadmap for quantum technologies, one of the possible roadmaps. But I like very much this picture because it shows these four great pillars of quantum technologies: communication, computation, simulation, and quantum metrology, sensing. And it shows that these four pillars are based on this very important basis, which is basic science. And they are purposed by engineering, control, software theory, education, and training. So this, for me, this is an example of a very interesting field of research, because it takes everything, you know. It's related to education and training. It involves engineering and control, software theory, and of course, it's all dependent on some very basic science. Now, today, I'm going to tell you about this pillar here, and I hope I'll convince you that this pillar is a very active one nowadays. Actually, maybe from these four pillars, this is the one which has more results, practical results, actually, nowadays. Now, of course, all of you know about how quantum sensing allowed the human beings to explore the early universe. Squeezing started to be implemented at LIGO, LIGO. And this is an article on that. And in fact, the application of squeezing to LIGO, and Bill Uru mentioned that or proposed that a long time ago, like use of squeezing in LIGO. Using squeezing in LIGO, you got the possibility of extending the region of the universe, which is found out, which is revealed by this interferometer. So you see this picture here refers to the observing run 3. That's how they define it. And in black here, you have the reference without squeezing. In green, you have the distribution of this strain noise with squeezing. So strain noise comes because when a gravitational wave arrives, it compresses one of the arms of this interferometer, it extends the other one, so it's a strain that happens, and there is a strain noise. Now, for the second observing run, the extension of observations was of the order of 100 megaparsecs. This third observing run consider the space between 100 and 140 megaparsecs, and it could do that thanks to this 3 decibels increase in sensitivity for observing, say, black gravitational waves coming from the collision of binary stars. Now, the fourth run started in May of this year, and now they plan to go to these limits here, 150 to 160, a little bit more than that, megaparsecs. So a whole new world will be opening, and squeeze states are very important in opening up this new world. Now, I'll give you some other examples of the application of quantum technologies later on. But I'll go back to the basics now and just define what we mean by quantum parameter estimation and what are the basic questions to be answered. First question, what's the proper metric to analyze the precision in the estimation of parameters? The parameters could be, for instance, the gravitational field. Are there fundamental limits? Is quantum mechanics helpful in reaching better precision? How to cope with the deleterious effects of noise? So these are important questions in this field. And I would say that people who work in this field have the same kind of obsession as Theodor Hensch, who got the Nobel Prize for his precise measurements, his great ideas. And the title of his Nobel lecture was Passion for Precision. Okay? So that is a very good sentence, a very good expression for quantum metrology today. Okay? Passion for precision. Now, this talk will have 5 parts. The first one will be an introduction, classical parameter estimation. Some of you have already heard me talk about that. I'll try to present in a slightly different way, and maybe for students who have not heard it before, it could be useful. Then I'll tell you about quantum parameter estimation, quantum metrology of noisy systems, where we have done some work, and precision limits for estimation of absorption as an example of quantum metrology of noisy systems. And finally, I will give you examples of useful applications that come from basic science and which are there nowadays. Some of them are being sold by companies. So, oh yes, and very important, I'll deal here with what we call local quantum metrology. So one wants to estimate a parameter confined to some small range. That's the case, for instance, of the LIGO, where you want to estimate the compression or the extension of the arms of the interferometer, but that's around they are very small displacements, or any detection of some, for instance, small magnetic fields. So these are typical quantum sensing problems. Okay? The other kind of quantum metrology is the one where you don't have any idea about the parameter. It is in some broad region, and you want to discover what it is. And then you use Bayesian analysis. Okay? We're not going to do this now. Okay? Now, so for parameter estimation, you have this general strategy. You first prepare a probe in a suitable initial state, you send the probe to the process to be investigated, such that the probe must be such and the process must be such that the final state of the probe depends on the parameter you want to estimate. Then you choose a suitable measurement of the final state of the probe, and you associate each experimental result with some estimation of the value of the parameter. So that's the general procedure. Okay, so it's an indirect measurement of the parameter. You send a probe to estimate the parameter. Now, this whole thing of quantum metrology, this whole field, is related to a very basic question, actually. And the question is this: how much the outcome probability distribution of an experiment changes by a change of the parameter? Okay. Now, in order to answer this question, we have to define the distance between two probability distributions. And there is a distance which was demonstrated in literature. It's called Hellinger distance. And this distance is defined by this expression here. Okay. Now, you see that, of course, if x is equal to x prime, this is equal to 0. And just reminding it to you, so pxk is the probability of getting an experimental result k if the value of the parameter is x. So here you change the value of the parameter from x to x prime, and then you have another probability distribution, and the distance between them can be defined by this expression. We can show that this definition satisfies all the conditions for a definition of distance, okay? which are written down here. Okay, so this is a true distance, say, between two probability distributions. Now, we can make a very simple calculation. We can find now the distance between two probability distributions. One is for the parameter x, and another one is for parameter x plus dx. You change the parameter a little bit. So you have to calculate this quantity here. And that's very easy to calculate. You can use even the derivative of this, or you can expand this term here. And you find that when dx goes to 0, the first order that shows up is this one. Okay? So it goes as dx squared. Now, you see that here you have the speed. X is not necessarily time, okay? Yes? Now, so look at this here. This is a kind of speed. It's a speed of variation of this probability here, actually the square root of the probability when the parameter changes. Okay? So this speed here defines a function of x, and this function of x is called the Fisher information. Okay. So the Fisher information is directly related, it's a measure, if you want, of the speed of change of the probability distribution as the parameter x changes. Okay, that's the Fisher information. Now, this is for the distance. I could also relate the Fisher information to the fidelity between the two distributions. And the fidelity is defined by this expression here. And you see that if x is equal to x prime, you have here p squared, square root of p squared is p, sum over k is equal to 1. Okay, so the fidelity is equal to 1 if x is equal to x prime.
Is
yes.
the capital X the random variable, or what this is?
X is a parameter.
It's just the one value.
It's a parameter which you want to investigate. Okay, so could be, for instance, the gravitational field.
Is it stochastic or deterministic?
It's actually deterministic. There is a true value for the parameter. For instance, you are measuring the gravitational field here. Okay, you make several measurements. You have a distribution of measurements, right? Now the gravitational field has some value which you don't know, but you'd like to find out. So that's a parameter that you want to find out.
And the capital P is a subscript K. Does it mean the probability?
It's probability of getting some value K when you measure, for instance, the gravity here. You not get exactly the true value of the parameter, you get the distribution.
Okay.
Okay, good. So that's the definition of the fidelity between two probability distributions, and you can easily relate the distance between two probability distributions to the fidelity. very simple exercise is given by this expression. And from there, you find that the fidelity between corresponding to different values of the parameters, so a distribution that depends on x, and a distribution that depends on x plus dx, when dx goes to 0, is given by that. So again, if you look at this expression, you see that since this is multiplying dx squared, square root of this is the speed of change of the fidelity. Okay, so again, the Fisher information is related to the speed of change of the distance between two probability distributions, or yet the speed of change of the fidelity. Okay, that's the Fisher information. Okay, but then you see that, the larger the speed, then the better should be the estimation of x. Because if you change x just a bit, the two distributions get far apart. So come on, it's better to estimate in this way. Okay, so this speed should be related to the precision of estimation of x. And this is indeed the case. And this was shown by these three people here, starting with Kramer and Rao, and then Fisher gave some important contribution. And what they show is that the standard deviation in the measurement of the parameter x is bounded below by this expression here, where this n here is the number of repetitions of the experiment. This is well known by many people. Okay, if you increase the number of experiments, the precision increases, and it goes to 1 over square root of f. Okay. Independent process of independent measurements. And f of x is precisely the Fisher information which we had before, which is calculated here for x equal to the average value of the measurements. Yeah.
Is there some assumption about the Gaussianity of the distribution in this?
I'm going now to that, not necessarily. Okay, no, but I will tell you what the Gaussianity will give to this. Okay. Yeah. So this is the result of Kramer and Rao. I'm assuming here unbiased measurements, which means that the average value is equal to the true value of the parameter. If you keep measuring gravity here, then the average of the average of the experimental results is equal to the gravity. That's the assumption. Okay, here. So by assuming that, we can demonstrate this inequality here. F of x is precisely equal to the expression I showed you before. Remember the velocity of the square root of the probability distribution. And it can also be written like that. That's a simple algebra here to show that this is equivalent to that. And as I mentioned before, this is the Fisher information. Okay? So what they did was to relate. It was not like I'm presenting here, but anyway, what they did implies that the speed of separation of the two distributions is related to the uncertainty in the estimation of the parameter x. So this is the Fisher information, and in fact, Fisher showed, and that comes the Gaussian states, that if you have Gaussian states, or then if n goes to infinity and the central limit theorem applies, this can be saturated, which means that inequality can become an equality. Okay? And this was shown by Fisher. Okay. Now, this is for discrete measurements, and then for continuous measurements, you can replace this expression by this one. Instead of a sum, you have an integration here. And now this is a probability density, which gives us the probability density of finding an experimental result psi if the value of the parameter is x. Okay? So that's classical parameter estimation. Not about now, what about quantum parameter estimation? Well, we just mimic what was done classically, basically. There are new points to consider. So again, precision in determination of the parameters should depend on the distinguishability between quantum states corresponding to nearby values of the parameter, as we saw in the probability distribution. But now we're talking about quantum states. Okay? Second, of course, measurement matters in quantum physics. So we should be careful about that. And the question that we must raise is whether it's possible to get better precision for the same amount of resources by using special quantum states. Now, what are special quantum states in this case? Well, say superposition of two states. It's a quantum mechanical thing. Squeezing, entanglement, ultra cold matter. Okay? These are all special inputs that you can use to estimate better subparameters, including, for instance, gravitational field or weak magnetic fields. What about resources? Well, that depends on the system you are looking at. That could be, for instance, the number of atoms in atomic spectroscopy, or the number of photons in optical interferometry, or the average energy of a harmonic oscillator, and so forth. Okay, so these are the resources that you have to consider in each case. Now, how then we go to from classical metrology to quantum metrology? And this was done by these people here. There is a book by Hellstrom, which is an amazing book on statistics. Okay. And what you do is straightforward generalization. So the Fisher information, again, is given by an expression like that, like in the classical case. Okay. Remember, psi are the values of the measurements you do, and x is the value of the parameter. Now, this probability density now is given by the quantum mechanical expression. Okay? So if the state of the probe is psi, that's the outgoing state of the probe, this operator here describes a measurement that you do on the probe. And the probability of finding some result psi due to this measurement is given by this expression, the average of this operator. Of course, since this integration of the probability should be equal to 1, the integration of this operator should be equal to 1, and this defines what one calls positive operator value measurement. It's an extension of von Neumann measurements in the sense that these operators don't have to be orthogonal among themselves. Okay? But so it's an extension. But they should be positive, semi-definite. I'm not going through these discussions here, okay, too mathematical. So this corresponds to a given quantum measurement, right? You choose a set of operators that define your measurement, and then you find this probability density. You define the quantum Fisher information as the ultimate lower bound for the uncertainty, obtained by optimizing this expression here over all possible quantum measurements. Okay? So that defines the quantum Fisher information. Now, if you give that to some graduate student who is starting graduate school, he may resign at that moment, you know, because come on, you want me to, you know, maximize this Fisher information over all possible measurements? How can I do that? No, this can be done. Okay, this can be done, and that defines the quantum Fisher information. And in fact, I find this very nice, that the quantum Fisher information, in fact, measures the distinguishability of the parameter-dependent probe states psi x and psi x plus dx. It is also the speed of change, and the expression is this one. It's like the classical expression. Okay, so this is the scalar product between the two states. So it's the fidelity, if you want, between the two states. And again, the fidelity, when you expand in terms of dx, the first term is this one. So the first term is 1, then comes this one, and this is the quantum Fisher information. So the quantum Fisher information is the speed of decline of the fidelity from the maximum value 1. Okay, so you have a system, you want to identify a parameter, then measure a parameter, so you send a probe through it. It could be, for instance, the absorption of light, the parameter. And I'm going to give you an example of that. Okay? Any further questions at this point? I love questions.
Well, I have lots of questions, but I was being nice.
Okay.
But may I ask?
Sure.
So in using the distributions, what if I tried to use something like a Wigner distribution, which went negative?
Very good. So first I was talking about classical physics.
Right.
Okay? No, this is quantum now. And the question you were asking was a question which I discussed with your former student, Wolfgang Schleich, some time ago at some PQE. And at that occasion, we did not get to any conclusion, and maybe there should be a conclusion. And the idea was precisely that of using the Wigner function probability for the Fisher information. Okay,
Right.
but at that moment we could not do it, but maybe it can be done. Okay, so good question. So now compare the quantum expression, which I just showed to you, with the classical expression we had before. You almost are tempted to replace the square root of p by psi. Right? So they are very similar. Okay? They are very similar. Now, if you don't have a pure state, if you have a mixture, then you can generalize that expression. And that's for the students who have already seen density matrix, density operators. Okay? You can show that there is a fidelity that you can define between two states of the probe, rho 1 and rho 2, that differ from the value of the parameter. For pure states, this definition becomes this one, which you know, that's fidelity between two pure states. And then you can show that the fidelity between rho of x and rho of x plus dx, again, x is a parameter, as dx goes to 0, goes to this expression. Again, the quantum Fisher information is here, now generalized for mixed states, not necessarily pure states. Okay? So that's the basis of what I'm going to tell you now. Now, for pure states, that maximization of Hall operators can be done. So, and in fact, the result is very nice and very simple. Suppose you have some initial state of the probe, which is psi 0, then a final x-dependent state, which depends on the value, on the parameter, could be a coupling constant, for instance, which I can write like this. So this is the evolution of the probe, which is dependent on the parameter. And this is a unitary operator. So I suppose there are no losses, and all of the states are pure. Then, according to this expression that I showed you, I could, using this, I could actually calculate what the quantum Fisher information is. And you see that here you have a derivative of this evolution operator. So what we get is the following, very simple expression. The quantum Fisher information is 4 times the variance of this operator here, calculated in the initial state of the probe. So this is like a Heisenberg operator, but it's not Heisenberg. I mean, it's an operator that depends on the value of the parameter. Okay? It depends on this evolution of the probe here. And this operator here is given in terms of the unitary evolution by this expression here. Now, I know that for some of you, if you look at this expression, you may think, what does it mean? Well, let's look at a simple case. Suppose the evolution of the probe is given by this expression here, where this operator O is independent of the parameter. Then by using this expression here, you find that this H is given by this operator here. Okay, so in this simple case, H is just given, is equal to the generator, if you want, of this transformation. And in this case, the Fermi-Rao relation becomes this one, the standard the standard variation of the parameter, so the square root of the variance, is bounded below by this expression, which involves now the variance of this operator. So that shows that I should maximize the variance in order to get better precision. And since the variance is calculated in the initial state, you better have an initial state that maximizes this variance. And I'm going to show you some examples in optical interferometry. So let's apply this to optical interferometry. We know that the number operator is the generator of phase displacements. Okay, so if you apply this expression here to a coherent state alpha, you get this coherent state with this phase displaced. So it's a phase displaced coherent state. This is the number operator again, and phi is a phase. So since I showed in the last slide that if you have something of the form e to the I operator times the parameter, then the quantum efficient information is just equal to 4 times the variance of the generator. The generator is the number operator. So a very simple expression. And if you have that, you can now write down the Kramer-Rao relation for this, which shows that the uncertainty in the phase is bounded below by this expression here, which involves the variance of the number operator. Okay, just application of Kramer-Rao. And perhaps some of you have already some ideas about this. I will go to that in the next slide, because you might ask, what about Heisenberg uncertainty relations? Next slide. Okay. So let's apply this to a coherent state. Now, for a coherent state, the variance is equal to the average number of photons. So I can replace this here by the average number of photons, and that will give me that the uncertainty in the summation of the phase is bounded below by this expression here, 1/2 square root of the average number of photons. Okay, so that's the result of the Kramer-Rao relation. Okay. Now, can we do better? Well, we can. Instead of using a coherent state, let's use this state here, which is called Noon state for obvious reasons, right? And this state tells me that this is a superposition of two states, one that has n photons in the upper branch of the interferometer, the other has n photons in the lower branch of the interferometer. Now, just do this calculation, calculate the variance of the number of photons in this state. You find that it's equal to n²/4, and therefore, in this case, the uncertainty in the phase is bounded below by this expression here, 1/n. Compare this with this expression here. You see that for the same average number of photons, you get a better precision here than here. Okay, so Noon states help you. Why? Because the variance of the number of photons in the upper branch of the interferometer is the largest possible variance. You have either 0 or n photons there. Okay, so that increases the precision. Now, these two results may remind us of some old question. And this is a facsimile of the Heisenberg paper on uncertainty relations. And in that paper, it has this commutation relation here between energy and time, which produces, according to him, an uncertainty relation between energy and time. Now, Pauli came afterwards and he said, come on, time cannot be an operator, because if time is an operator, then the evolution operator, which I wrote before, e to the I, h, t, if time was an operator, then it would be an operator for displacement of h for the energy. And it could displace the energy to the infinity or to minus infinity. So the system would be unbounded below and not stable. Okay, so that was the argument of Pauli. Now, about the number phase uncertainty relation, many people try to define phase operators. Lots of suggestions, interesting suggestions. But my point here is that that's not needed. Okay. In fact, from this Kramer-Rao relation, for both cases, you see that if H is the Hamiltonian, then the evolution operator will be like that. T is a parameter here. And from the Kramer-Rao relations, I would get the delta T, or the precision in summation of the time, should be bounded below by this quantity. Again, the square root of the number of trials, and then the standard deviation of the energy. And from that, for just one trial, you get that delta E, delta T should be larger or equal to 1. Uncertainty relation between time and energy. Again, for the phase, I have just done that for the interferometer. Kramer-Rao will tell me that delta phi is larger or equal than 1 over square root of n times the standard deviation of n. And again, this will show me that delta phi delta n is larger or equal to 1 if the number of trials is equal to 1. Again, an uncertainty relation between phase and n. And here is wrong, of course. This should be 1 over 2. So you see, this is Kramer-Rao, not Heisenberg. Okay, so I don't need to define a phase operator here. I don't need to define a time operator. Okay, so I think it should be understood like that. Now, I told you about pure states, and that's easy, okay, because we got that the Fisher information, quantum Fisher information related to the variance of the operator. Now, what about the general case? Oh, you asked about the title of the book. There it is. See, it's here. Hi. Quantum detection estimation. Oh, you found it. Okay. And then there is a book by Rolevo also, which is here. Okay. 1982. Okay. And even the article by Brownson and Case. Okay. Now, so one can show, and if you don't want to follow this in detail, you can disconnect for 2 minutes and then connect again, okay? Because I'm going to use that, but if you believe me, you don't have to follow this. So it can be shown, it's shown here, that the general expression for the quantum Fisher information can be written like that. And that's for a mixed state noisy system, okay? So the quantum Fisher information is given by this trace of the density operator of the probe times this operator here. And this operator is defined implicitly by this expression here. Okay? Now, that means that you need to know the density operator of the probe in order to find the operator. Now, this operator has this funny name, symmetric logarithmic derivative. And let me try to justify this name to you. If you had classical physics, if rho commuted with L, then we could write this as like this, right? So assuming that L is not a function, not an operator. And now I can find that L of x is given by this expression here. But this expression is the derivative with respect to the parameter of the log of rho of x. Okay? That's why this is called symmetric logarithmic derivative. In the quantum case, we have to be careful about the ordering of L and x, L and rho. Okay? Now, from this expression here, you find the matrix elements of L. They are given by this expression here. You just take the matrix elements of this expression in the basis of eigenvalues of rho, and you get this expression here. So in principle, you can calculate L. And if you can calculate L, you can find the quantum Fisher information for any system. Now, of course, if you have a system with infinite dimension, finding the eigenvalues of the density operator is not, in general, an easy task. Okay? So we need some other methods in general. Now, what we can show is that analytic expressions can be obtained for Gaussian states, again, or for low-dimensional Hilbert spaces, because then you have just a matrix here, which is at most 4 by 4, and you can solve it. Okay, like, for instance, 2 qubits. Right. Now, there is estimation theory of multiple parameters. I'm not going to talk about it now, okay? But again, these are classical parameters. If you want to estimate a state, the name of that is a quantum tomography. That estimates the state, and that can be done. I'm not going to deal with that today, okay? So this is not tomography. Now, this is for any system. It could have noise here, could have anything. A rho of x is the density operator of the probe after it interacts with the system. Okay? And that interaction depends on some parameter x, and I want to estimate this parameter. Okay? So now we are in this other land, which is the land of noisy systems. Okay? And things get more complicated, but there are some simplifications that can be done. Okay? So now we are going to talk about quantum metrology of noisy systems. Okay? And just to realize how important this is, I mentioned before to you that a noon state was the best possible state for estimating a phase of an interferometer, right? Now, suppose you have a noon state here, and there is some absorption here, so you can have loss of photons here. Now, if only one photon is lost, this coherent superposition will become either this one or this one, depending on whether the photon is lost from here or from here. Now, this is not a coherent superposition anymore. This is a mixture. And there is no phase information here. So the loss of a single photon does not allow you to get any phase information if you have a null state, which means that you are extremely unstable for phase estimation. Okay. Now, so that's why we became interested in actual noisy systems. What can we do about it? And in fact, what is happening with null states is more general. It's related to the fragility of entanglement under noise. And our group has done lots of work on that, including the one that was mentioned in the presentation, right? This is very good for being presented in the Halloween field, right? Entanglement sudden death. So it's a Halloween paper. And then we had another paper on determining dynamics of entanglement, but everything here was done with this aim of understanding how fragile entanglement is when it is interacting with the environment. Okay. And if you're interested, I can give you the references afterwards. Now, but then we realized that precisely because the entanglement is fragile, it could be very good for estimating parameters, right? Like noisy parameters, because it's fragile. So it changes fast when you have some interaction with some parameters. So I'm going to tell you about this, and that actually also explains why entanglement is still considered a very interesting property, especially to estimate noisy channels, parameters of noisy channels. Now, so the idea we had back in 2011 was the following. Suppose you have some system here interacting with some environment. So it's a noisy system. So you then make a trick. You give it some initial state of the system and some non-unitary evolution of the system. We define now a unitary evolution in S plus E. We include the environment into the game. Now it's a unitary evolution which will apply to the state of the system and the initial state of the environment. Okay, so that's unitary. But that's not any unitary. We want this unitary evolution to be such that if I trace out the environment, I get the non-unitary evolution of the system. Okay, so it's a concoction. I have to find out an environment such that when I trace it out, it gives me the non-unitary evolution of the system. But the evolution of everything is unitary here. Now, then it's easy to understand that the quantum efficient information of the system, which is obtained by calculating the maximal measurement, or the measurement that maximizes the efficient information if you don't do anything to the environment, should be smaller or equal than this other efficient information, which corresponds to S plus E and corresponds to measurements made on S plus E. In other words, if you measure on S plus E, you should get a larger efficient information than if you measure on S alone. Okay, because you have more possibilities and you want to find the best possible measurement that will maximize the efficient information. So this is an upper bound for the efficient information of the system. Okay? And what we have shown in this paper here is that this bound always can be attained. There is always a purification, which is this thing here, such that this upper bound of the quantum efficient information is equal to the quantum efficient information of the system. Okay, so that's a funny way of finding the quantum efficient information of a noisy system or a system which is interacting with the environment. You calculate this upper bound, and you pray that this upper bound will coincide with your quantum efficient information. Actually, you don't pray. You have to use physics to find some upper bound that is convenient. I'm not going into this detail now. And we have applied this to many problems. This is the quantum speed limit that I mentioned before. Okay? And other problems also showing that this upper bound can actually be very useful, and it avoids us to diagonalize the density operator of the probe in infinite spaces, infinite dimensional Hilbert spaces. So that's the idea. And let me give a very simple example of the utilization of this bound. Suppose I have a slab here with some material, and I want to estimate the absorption of this material. Okay. Typically, noisy system, okay, non-unitary. Okay. What do? Well, I replace the system here by a beam splitter. Okay. Of course, if I look at the incoming field and the outgoing field, the beam splitter simulates an absorption material, right? Because part of the incoming beam is reflected here. And here I have the vacuum, okay? Nothing is injected here, only something is injected here. So this simulates this master equation here. And of course, this is the global system plus environment. B is the environment mode, A is the environment of the system. Okay? And now I can calculate the quantum Fisher information for this whole thing. That's the quantum Fisher information for a beam splitter. Okay? It can be done. Okay? And I'm not going to go into details here because there are too many equations. But anyway, you can find the upper bound for the quantum Fisher information by looking at the quantum Fisher information of this unitary evolution here. And the upper bound gives you a very simple expression, which is this one. Is the average number of photons in incoming field divided by this expression here, alpha times 1 minus alpha. And this gives you a precision in the estimation of alpha, which is given by this expression here. Okay. Now, this is an upper value for the quantum Fisher information, and it's possible to demonstrate that this upper bound is actually achievable if you send a Fox state here and do photon counting at the exit of the beam splitter here. And if you want to know more about that, you go to this paper here, where you use this kind of technique to estimate damping constants and temperature of slabs. Okay, just by using this kind of method. Okay, so by using this, we found an expression actually for the quantum Fisher information of this system here, because with a Fox state coming in, we saturate this bond. So that's the quantum Fisher information when you have an incoming Fox state. So if you give me a slab and you ask me to estimate the absorption of that slab, then of course, if you're an experimentalist, I'll tell you, okay, that's easy, give me a Fox state. And now I see the experimentalists start laughing, okay, because Fox states are very difficult to produce. You can produce a 2-photon Fox state, more than that's complicated, right? But there's a trick. There's a trick, and the trick is the following, is to use squeeze states. So this paper is submitted for publication, and we have this situation here. Some slab, some incoming field, some outgoing field, some absorption coefficient here. And I'm going to compare the classical situation with a very curious quantum situation. The classical limit I get with a coherent state incoming here. And then I can do a classical calculation, very simple to do. The intensity out is 1 minus alpha times the intensity in. So from this, I can calculate the uncertainty in alpha, okay? And I get this expression here for the uncertainty in alpha. So this is the uncertainty in the absorption parameter corresponding to a classical situation, coherent state coming here. Now, we have another option, which is this one. We have here an optical parametric amplifier. This optical amplifier produces a squeezing state, which is a 2-mode squeezing state. Now, mathematically, this squeeze state corresponds to applying this operator here. You see that it's 2-mode. Remember the beam splitter? But the beam splitter was adaga B. Here, adaga B daga produces a squeeze state, okay, applied to the vacuum. Okay? So it produces this kind of state. And this is the squeeze state that is produced. You have a 2-mode vacuum state in the entrance, so nothing coming in. Okay? You have a bumping laser here. And then at the output, you have the squeeze state here. Now, there is a very funny property of squeeze states. We can expand them in terms of Fox states in this way. They are paired Fox states, correlated Fox states. So when you look at this, you think, come on, maybe there is some possibility of using a Fock state for estimating the absorption by using squeeze state. And in fact, this can be done. This can be done. So we use this squeeze state here. We are theoreticians, so I should say we propose using this squeeze states, okay? And then what kind of measurement are you going to do? Well, we do this photon counting, joint photon counting of the two beams that come out from this optical parametric amplifier. And the trick is the following. By measuring this beam here, I know what's the probability distribution of the incoming photons here, because they are paired. Okay? And by measuring simultaneously this, so I know how, if I measure, for instance, M photons here, I know that M photons came here, and that's a Fock state. So the summary of this thing is that this joint distribution can be written like that. This is the initial distribution of photons here or here. And this is the final distribution of photons here. And the joint probability is given by this expression. Now, from having the joint probability distribution, I can calculate the Fisher information. It's given by this expression. I don't want to bother you with the details. I just want to get to the final result, which is a very nice final result. Okay? So the final result is that the Fisher information is, in this case, is the Fisher information corresponding to M, a Fock state with M photons coming through the absorber. And this average over the distribution of initial photons, which can be read from here. Okay. So this is the Fisher information corresponding to this joint measurement. And if you calculate this, you find that this expression is this one. This is just the average of the number of photons coming into the system. And this gives, therefore, this expression here. Now, if you remember the exercise we did on the beam splitter, this is precisely the upper limit for the beam splitter, which was obtained using a Fock state. Now, so that's what I was just saying. This is very resilient to decoherence because this leads to the same result. Okay. Now, this is the result we get comparing the classical result with this quantum result here. Green is the classical result for the estimation of alpha. This is for small absorption, 0.05. And red is the quantum result, which is given by this expression here. And that's the beam splitter result. And for slow average number, for low average number of photons, that's the result we get. The advantage here is 5 decibels. Okay, so that's the result with this photon counting. And we did one thing more, which is instead of doing joint photon counting, which is also difficult experimentally, we do some inverse transformation here. There's a kind of time reversal strategy. We consider here an optical parametric amplifier, which is the inverse of this one. So it unsqueezes the beam if there is no absorption here. So if there is no absorption, you come in with the vacuum state, you go out with the vacuum state. It's like setting the pointer of a measuring apparatus at 0, and then you count the number of photons here, the total number of photons here, and you calculate delta alpha. And for small absorption, the red line is the result obtained from the quantum Fisher information from the joint photon counting, and this traced blue line is the one corresponding to measure the total number of photons here. So you see that that's a nice strategy. You make the inverse transformation here, and instead of doing joint counting, you just count the total number of photons. Okay, and you get practically the same result. Okay, so that's a time reversal strategy that works fine in this case. Now, I have 2 minutes to show a bird's eye view of some useful applications. Okay?
Without questions.
Without questions, but then I'll be glad to answer the questions afterwards. Of course, you all know that, right? the authors are here. So you can use squeeze states to increase to get better images. So this can also be used to imaging. And this is what they got here in Texas A&M. This is a slab of crystal, and you send light through it, normal light. You can actually see that this slab was here by looking at these lines here. However, if you use squeeze light, you get a much better contrast of the image. Okay? And that's a nice use of squeeze light for microscopy. Okay? Now, improving atomic clocks, you know, I was actually looking at this for this talk, okay? And it's amazing. You know, the progress in this, it's really amazing. So lots of papers being published recently involving, you see, quantum logic clock, entanglement on an optical atomic clock transition. Look at this, resolving the gravitational redshift across a millimeter scale atomic sample. So they can, in the space of 1 millimeter, in measuring the frequency of atoms here and here, they can find a difference in the gravitational field. Okay, so this is very interesting because they can check general relativity theory. And actually, this expression here, which compares the fractional frequency measurement, which is 10 to the minus 21, actually, they compare that with the general relativity expression, which is the variance, how the gravitational potential change divided by c squared. And there is an alpha here. Alpha is the correction to general relativity if it shows up. Okay, so they can measure this kind of thing. Okay, so it's an amazing, amazing experiment made by Junier there. And in several, you see, entangled optical atomic clocks show up here. Optical lattices are being used a lot to do this kind of experiments. Programmable quantum sensors. This is a paper that involves Peter Zoller, Heine Blatt. So they can program quantum sensors, including for quantum metrology, for getting better quantum metrology. So you see, I'm not just talking about things that Hellstrom wrote a long time ago. These things are happening now. They're happening. Lots of them are happening. Quantum gravimeters are being sold. This is a gravimeter from IXBlue. It measures gravity with a sensitivity down to 10 to the minus 9 G. Okay. Now you may ask, what is 10 to the minus G? What is it good for? Well, I took this from this side here. There's another company that is selling gravimeters. I'm careful to mention both, otherwise you think that I'm paid by one of them, right? So, and now they show this, which is very interesting. So sensitivity of 10 to the minus 6 is good for finding mineral deposits, like oil, water, and things like that. Volcanic activity, you need this sensitivity. Underground burial chamber, archaeology, you need that. Small sinkhole, it's between 10 to the minus 8 is here, and now they have 10 to the minus 9 G, which is amazing, so they use quantum sensing for gravity cartography. And actually, quantum accelerometers have the same principle of working as quantum gravimeters, actually, very similar. But again, lots of new progress. They even have compact cold atom interferometer, entanglement enhanced optomechanical sensing that can also be used as accelerometer. And you see that a quantum prototype was tested by Royal Navy, and it offers, according to them, the future promise of GPS-free navigation. So the Navy is very much interested in that, because if they go underwater, they don't have access to GPS, and even if they had, they would not like to exchange signals to GPS, because it would be bad for them, right? So lots of interesting things are happening in this field. Quantum magnetoencephalography, which is amazing too. And what I find amazing, you see the role of basic science. This paper was written, Serge doesn't know that I found this paper. This paper was published in 1969. At that time, I think Dupont, Roch, and Serge were students of quantum ecology. Okay.
Yeah.
They were students of him, and they showed that they could detect very weak magnetic fields of 10 to the minus 9 Gauss by using the zero field level crossing resonances of rubidium. So they are level crossing, and if you have a very small magnetic field, you can remove that crossing, and the system starts to absorb light that goes to it. So again, amazing. Many years afterwards, in 2003, there was this proposal talking about a sub-femtotesla multi-channel atomic magnetometer. That means half of 10 to the minus 11 Gauss. And the theoretical limit for this system is 10 to the minus 13 Gauss. So they're trying to remove extra Gauss, extra noise, and so forth. Okay. So amazing progress. This is the magnetoencephalography made on this lady here. And you see, this is much better than the big thing using squeeze that needed to be refrigerated. This does not need refrigeration. You know, the principle is just this one. You have rubidium atoms in a cell, which was already talked about here. You have rubidium atoms in a cell, and when a magnetic field comes in, the medium becomes absorbed where it was not. So you can measure the absorption, and with that you can measure the magnetic field. Okay, and this can be done in a very small ship. Okay, so these are ships that are distributed around the head of this woman, and in fact, you know, you have to consider the neurons firing in the brain. They have an associated magnetic field signal on the scalp surface, lasting a couple of milliseconds, okay? and a few hundred femtotesla amplitude. So you really need this sensitivity here, and you need to measure it fast. So you cannot count on the factor 1 over square root of n, repeating the measurements. Single shot measurement, and that's being sold now. Q-spin cells, for instance, and it's based on this paper. So amazing thing also. Oh yeah, now they have ship scale atomic devices, and you have ship scale atomic magnetic, ship scale magnetoencephalography. Okay. So and finally, I know some people work on this here. Nitrogen vacancy centers for magnetometry. Also, the new results on that. This is from 2020. This is from 2022. So you have they increased the precision of that, and by doing that, they can scan, for instance, in this case, in-plane magnetic fields. Okay. And that's even used for medical industry to localize magnetic nanoparticles in a body, for instance. Now, and finally, nitrogen vacancy center for gyroscopes. Gyroscopes. And again, new results here. Well, 2021, nitrogen vacancy be used for gyroscopes. And these are two more recent papers on that, demonstrating diamond nuclear spin gyroscope. So lots of possibilities. I think there is much more to do. And as I mentioned in the beginning, you know, it's nice to work in this field because it has some basic things. You understand time energy uncertainty relation, number phase uncertainty relation, and then there are some very useful things that are being produced. And I think it's very much.